In this lecture video, we're going to be looking at the normal distribution, also called the Gaussian distribution. The sample space of the normal distribution is the entire real line. This expression here, given in the middle of slide 320, is the general form of the PDF for the general normal distribution. The distribution has two parameters, denoted typically by mu and sigma squared. And when we want to communicate the fact that a random variable x has a normal distribution with these two parameters, mu and sigma squared, then we will typically denote it in an abbreviated way like this. Or we might even abbreviate it a little bit more and just use the capital letter N rather than the full word normal. Now we're going to be looking in a fair amount of detail at this distribution. We're going to be looking at the cumulative distribution function. We will be deriving the mean of the distribution, the variance and standard deviation, as well as the skewness and kurtosis coefficients. And we will also derive the moment generating function. And it's actually from the moment generating function that we're going to derive the mean, the variance, and the third and fourth central moments, from which we get the skewness and the kurtosis. So we're going to start off with a special case. So consider the function with domain the real line, given by this expression here. And so you see here we have 1 over the square root of 2 pi times the exponential function evaluated at negative z squared over 2, where z is the argument to the function, and it can be any real number. Now the question is this a valid PDF? And I would point out that both 1 over the square root of 2 pi and the exponential function evaluated at any value, those two components are obviously positive, and so the product of those two positive numbers will be positive and therefore non-negative. And so it follows that this function f is non-negative for every real z. And it can also be shown that if we integrate this function over the real line, then we get 1. Now, we're not going to do that in this course because it takes a little bit more calculus than what is typically covered in Calc 1. And so we'll just take this as given. It's a given result, that when we integrate this particular function over the entire real line, that it integrates to 1. So because of those two facts, because this function is non-negative for every value of z on the real line, and the function integrates to 1 when we integrate it over the real line, then it satisfies the two conditions that are required in order for a function to be a PDF. And so this function is indeed a valid PDF. Now let's let the random variable z be a continuous random variable with PDF given by this function f as we've defined it on the previous slide. This particular distribution is a special case of the more general normal distribution. We're going to consider this special function PDF first and derive several properties of this special case distribution. And then once we've done that, we're going to consider the more general, normal distribution and use what we've learned about this special case to derive the corresponding properties of the general normal distribution. And so let's first consider the CDF of this special case. Let's denote the CDF by cap f. And so for a given real number z, the CDF evaluated at that value of z is by definition the probability that the random variable cap z is less than or equal to the argument little z. And you know that since we're dealing with a continuous random variable, the way that we get this probability is to integrate the PDF from minus infinity up to the value of little z. And so this turns out to be the integral from minus infinity up to little z, this function here. And so this is the function f, this is the PDF. And I've got to use a different letter than z as the variable of integration, so I'll use t here. And So this is the integral expression that would give us the value of the CDF at any given real number z. Now the problem is that there is no closed form expression for this integral, and so this is really as far as we can go with the derivation of the CDF at this point. Now we'll talk more about the CDF a little later, but we really can't go any further with it at this point. Now the moment generating function technique is going to be used to find the raw moments for the distribution of this random variable z, and so let's take a look at this. So we will now derive the moment generating function, or the MGF, of the distribution of z. Now remember that the moment generating function, if it exists, is given by the expectation of this special function, the exponential function evaluated at t times the random variable, in this case z. Now, in order for the moment generating function to exist, this expectation has to exist for every value of t in some interval around 0. Now, it doesn't matter how small the interval is, there just has to be an interval around 0 such that this expectation exists for every value of t in that interval. So the first thing we need to do here is derive an expression for this expected value. We've got to perform the integration and see what we come up with. So by definition then, the expected value of the exponential function evaluated at t times z is going to be the integral over the real line of the function or the exponential function t times z times the PDF. And so we need to replace f of z with the expression that it's equal to. And so here we have the exponential function evaluated at t times z times, and then notice that we also have in this product the exponential function over here. Now, using properties of exponents, we can combine those two. Remember that when you multiply two expressions, two bases raised to exponents, that when they have the same base, the exponents add. And so that's what we're doing here. Okay, so this integral is equal to this integral. This expectation is equal to this integral if we can somehow find a way to evaluate it. Now, the strategy we're going to use is to see if we can rewrite this integrand in some way that will make it easier to integrate. So let's consider the expression in the exponent of the integrand. All right, and so let's consider this function right here. Okay, and see if we can rewrite this in some way. And basically what we're going to do is we're going to complete the square. And so when we do, we see that this expression here, which is the exponent of the integrand, can be written this way. And so we can rewrite the exponential function evaluated at this expression as the product of the exponential function evaluated at this expression here times the exponential function evaluated at t squared over 2. Now that's helpful because when we replace this back into the integral, we see that the second term of the product of the integrand, the exponential function evaluated at t squared over 2, does not depend on the variable of integration. You see, it does not depend on z. And so we can pull that thing all the way out of the integral. And so what we're left with having to evaluate here is the integral over the real line of the exponential function evaluated at this expression here. Now this almost looks like the function f that we started with, but not quite because we have z minus t instead of just z. But we can perform a change of variable, letting y equal to z minus t. And so when we do that, we see that this integral right here, okay, evaluates to 1. And so this expected value that we're computing is going to be the exponential function evaluated at t squared over 2 times 1. And so here is the expected value of e raised to the tz power. it's e raised to the t squared over 2. Now, this exponential function involving t, and in particular t squared, exists for all t on the real line. And therefore, it exists for all t in some interval around 0. And in fact, it exists for every interval, for all t in any interval around 0. And so we can just pick any interval that we want. Okay, so we could look at the interval from -1 to 1, and we know then that this expectation exists for all t in this interval. And so because of that, it follows that the moment generating function for this distribution exists and is equal to this exponential function evaluated at t squared over 2. So we can use this moment generating function to now generate the moments for this special case normal distribution. We do that by calculating the derivatives of the moment generating function, the first, second, third, and fourth derivatives, if we want the first 4 raw moments. And so you can very easily calculate these derivatives, and then what we do is we evaluate each of these derivatives at t equal to 0 in order to get the corresponding raw moment. So to get the first raw moment, the expected value of z, we evaluate the first derivative of the moment generating function at 0. And so when we plug 0 in for t in this expression, we see that we have 0 times the exponential function evaluated at, would eventually evaluates to 0. So that would be 1. So we have 0 times 1, which is 0. To get the second raw moment, we evaluate the second derivative of the moment generating function at 0, and we get 1. So the second raw moment is 1. To get the third raw moment, we evaluate the third derivative of the moment generating function at t equal to 0. And again, that is equal to 0. As you can see up here, if we replace each t with 0, we're going to get 0 there. And then finally, to get the fourth raw moment, we evaluate the fourth derivative of the moment generating function at 0, and we get 3. Now, using those results, we can also very easily get the second, third, and fourth central moments of the distribution of z. And we don't even have to use the expansion formulas because in this case the mean of the distribution is 0. And so the second central moment of the distribution of z, which you'll remember is the variance of the distribution, is equal to 1. The third central moment is equal to the third raw moment, because the mean is 0. And so the third raw moment we saw to be 0, and so that the third central moment is also equal to 0. And then finally, the fourth central moment is equal to 3. And so we find now the skewness coefficient for the distribution being equal to 0. So it's a symmetric distribution. That's what that tells us. And the coefficient of kurtosis for this special case normal distribution is 3. Now let me just stop here and talk just a second here about kurtosis. And I believe I mentioned this in a previous lecture, but if not, I want to make sure that I cover it here. It's fairly clear how to interpret the mean. It's a measure of location, where the distribution is centered on the real number line. Remember that the mean can be thought of as the center of mass of a distribution, the balance point for that distribution. So that has a fairly easily understood interpretation. The variance of a distribution is a measure of dispersion or variation, and it's a measure of how spread out a distribution is. All right, and so we could use either the variance or the square root of the variance, which is the standard deviation, and it has the same kind of qualitative interpretation. It's a measure of variation or a measure of dispersion. The greater the standard deviation, the more spread out the distribution is, and vice versa. The skewness coefficient has a easily understood interpretation. If the skewness coefficient is 0, that means that the distribution is symmetric about the vertical line going through the mean. If it's non-zero, then that means that there's some skewness in the distribution, and if the skewness coefficient is negative, then that means that there's left skewness in the distribution. And if the skewness coefficient is positive, that tells us that there's right skewness. And then the magnitude of the skewness coefficient gives us, or tells us how, gives us the degree or the magnitude of the skewness in a graph of the distribution. But now, what does the kurtosis mean? I mean, we really haven't used that. We've calculated it in several examples, but we really have never used it. Well, now we're in a better position to use it, or at least try to interpret it. Typically, the way that the kurtosis is used is that the kurtosis of a distribution is compared to the kurtosis of a normal distribution. And so some distributions have less kurtosis than a normal distribution. Some distributions have a greater amount of kurtosis than the normal distribution. You'll remember that when we first talked about kurtosis, we described it as being a measure of the heaviness of the tails. And so if a distribution has a kurtosis that is greater than that of a normal distribution, what that's telling us is that it's got heavier tails than a normal. And when we say heavier tails, what we mean is that there's more probability out in the extremities of the tails than there would be in a normal. And so it's more likely to see extreme values with a heavy tail distribution than it would be with let's say, a normal distribution. And so that is typically how we're going to use the kurtosis when we evaluate it, or when we approximate it or estimate it based on data for a given population. So we'll talk more about that later. But for now, we just realized that this special case normal distribution has a kurtosis of 3. Next, we're going to consider the general normal distribution. And so to do this, we're going to create a new random variable, which we'll call x, from the random variable z, which is our special case normal random variable. And we're going to construct this new random variable from z using a linear transformation. In particular, x is equal to a times the random variable z plus b, where a is any non-zero real number, and b is any real number at all. Okay, now, since the sample space of z is the entire real line, and since we're getting x from z via a linear transformation, the sample space of the new random variable x is also the entire real line. Now, to find the distribution of x, we're going to first find the CDF of z. This says x here, but it should say, no, this is correct. To find the distribution of x, we're going to first find the CDF of x. And then once we do that, we're going to find the PDF of x by differentiating the CDF. So let's denote the CDF by cap G. Now we're using capital G because, remember, we've already used the uppercase letter F for the CDF of the special case normal random variable z. So the CDF of x is going to be denoted by cap G, and then so we will denote the PDF of the distribution of x by lowercase g. Now, there are actually 2 cases to consider in this framework, in this setup, and the 2 cases depend on the sign of a. Remember, let me go back to the previous slide, we said that a is any non-zero real number. So a could be positive or a could be negative. So we're going to first consider the case where a is positive. So the CDF of x, evaluated at a real number little x, is by definition the probability that the random variable x is less than or equal to the argument little x. And because x is equal to a times z plus b, we can replace x by that linear function of z in this probability statement. So the CDF of x evaluated at little x is equal to the probability that a times z plus b is less than or equal to the value of little x. Now I can rearrange things here inside the parentheses by subtracting b from both sides and then dividing both sides of the inequality by a. And when I do that, because a is positive, the direction or the nature of the inequality stays the same. And so this is why we need to consider the two cases, because when we divide through both sides by a, we need to know whether a is positive or negative, because the effect on the direction of the inequality will be different. Now, the probability that the random variable z is less than or equal to this expression, x minus b over a, we recognize as just being the CDF of z evaluated at this quantity here. All right? And so remember cap F was the CDF of z. And so what this says is that the CDF of x evaluated at little x is equal to the CDF of z evaluated at little x minus b over a. Now, once we have that CDF, and let me just point out, we really don't have to express it with any more detail than we have right here, at least at this point. So now we're going to find the PDF of x by differentiating the CDF. And so the PDF of x, which is denoted by little g, lowercase g, is given by the derivative with respect to x of the CDF of x. And so we have the derivative of cap F evaluated at x minus b over a. And remember that when we take so we're going to use the chain rule here. You'll want to remember back to calculus using the chain rule. But remember when we take the derivative of the CDF of z, when we take the derivative of cap F, we get little f. And then we also have to take the derivative with respect to x of this expression here inside the parentheses. And so when we take the derivative of that with respect to x, then that gives us 1 over a. Okay, so that's where that shows up right there. So the PDF of x can be expressed in terms of the PDF of z in this way. Now, in this case, you'll remember that a is positive, and so it follows that a is equal to its absolute value. And so we can write the PDF of x in this way. G of x is equal to 1 over the absolute value of a times the PDF of z evaluated at x minus b over a. Now, case 2 is the situation where a is negative. Okay, and so again, we're going to start off g of x, cap g of x, the CDF of x evaluated at little x, is by definition equal to the probability that x is less than or equal to little x. And again, that's equal to the probability that a times z plus b is less than or equal to x. Now again, we're going to rearrange things inside the parentheses by subtracting b from both sides and then dividing both sides of the inequality by a. But when we do that, because a is negative, the direction of the inequality changes from less than or equal to greater than or equal to. Now, by the complement rule, we can rewrite this probability as 1 minus the probability that z is strictly less than x minus b over a. And because z is a continuous random variable, remember, in that case, we can change the inequality from strict to non-strict. And we want to do that because this probability here is just the CDF of z evaluated at x minus b over a. So again, we have the CDF of x expressed in terms of the CDF of z, but in a slightly different way because in this case, a is negative. Now again, we're going to differentiate the CDF of x in order to get the PDF of x. And so when we do that, notice that we have, and let's look at this third line, the negative of the PDF of z evaluated at x minus b over a times the derivative with respect to x of x minus b over a, and that would just be 1 over a. And so we would have negative 1 over a times f evaluated at x minus b over a. But I can associate the negative with a down here, and that's helpful because in this, remember that we're dealing with a situation where a is negative. And so the negative of a negative number is positive, and so for that reason, negative a is equal to the absolute value of a. And so again, we can rewrite or we can express the PDF of x in this way. And if you go back and look, this is the same exact way we expressed it in the previous for the previous case. And so it follows that for all non-zero a, the PDF of the random variable x being equal to a times z plus b is given by this expression here. Now, at this point, we're going to expand or write out what this function f is evaluated at x minus b over a. And so this is what that function would look like. Okay, and we can write it in a couple ways. You'll typically see it written this last way in most statistical textbooks, but sometimes you'll see it written in that second form as well. And this function, this PDF, regardless of which of the two you choose to use, this is the general form of the PDF of the normal distribution. Now, you'll notice that there are two parameters in this PDF. And the parameters are the values or the symbols in here other than x. X is the argument. It's the value at which we are evaluating the PDF. But there are some other constants in here that we need to make note of, in particular a and b. Now, a shows up here under the square root sign, and it shows up here in the denominator, both in terms of a squared, and then b shows up here in the numerator of the exponent. So those are the two parameters of this distribution. So the questions would be, what do these parameters represent? Do they have meaningful interpretations? Now, to answer these questions, we're going to derive the moments and the various characteristics of the general normal distribution, and hopefully that will shed some light on what these parameters represent. Because if we are able to come up with the mean, the variance, the skewness, and kurtosis, then at least some of these ought to depend on A and B, and that may shed some light on what A and B represent. Now, to derive the moments and characteristics of the general normal distribution, we're going to make use of the fact that x is derived from z via this linear transformation, a times z plus b, in conjunction with what we've learned about the moments and the characteristics of the distribution of z. Remember that for the distribution of z, we found the mean, the variance, the skewness, and kurtosis. And to find those, we had to find the first four raw moments. And so we're going to be able to take what we know about the distribution of z, combine it with the way in which we define x in terms of z, and that's going to make it very, very easy for us to find these characteristics of the distribution of z. The good thing about this is we're not going to have to do any more integrations at this point, in order to get these distributional characteristics. We're going to use the linearity property of the expectation operator along with the work that we've already done to find these characteristics of the special case distribution of Z. And so when we do this, and you can read along through here, I'm not going to read aloud all these steps, okay, but we see here that the mean of the distribution of X is this constant B. Okay, so the parameter B in this PDF of the general normal distribution, the parameter B is the mean of the distribution of X. Finding the variance of the distribution of X, well, again, going through these steps where we write out what the variance represents, it's the second central moment, and then replacing X by what its representation in terms of Z, and also the fact that we now know that the mean of the distribution of X is equal to B, and we get simplification here, and we find out that the variance of the distribution of X is A squared. So remember that in defining X from Z, A was the slope of that linear relationship. And so A squared turns out to be the variance of the distribution of X. The absolute value of A turns out to be the standard deviation of the distribution. So we have found what A squared and B in this general representation, or this PDF of the general normal distribution, we found what A squared and B represent. A squared is the variance and B is the mean. And so we could immediately go back and re-express or rewrite this PDF of the general normal distribution, replacing A squared and B with a notation that corresponds to the variance and the mean respectively. And so we can see here, this is the general form of the normal distribution that we've given right here. Now let's continue on, and let's derive the skewness coefficient for the general normal distribution. And again, using the same kind of argument that we used for the second central moment, we find that the third central moment is 0. The third central moment is 0. The variance is positive. All right, and so the skewness coefficient is well defined, and it is equal to 0. And then finally, we can find the kurtosis of the general normal distribution. So we first find the fourth central moment, and we find that that's equal to 3 times a to the fourth power. All right, then to get the kurtosis, we divide that fourth central moment, 3 times a to the fourth. We divide that by the square of the variance. Now remember that the variance was a squared. So we have 3a to the fourth over the square of a squared. Well, that denominator is just a to the fourth, and so the a to the fourth upstairs and the a to the fourth downstairs cancel each other out. And so we see here that the kurtosis of the general normal distribution is again 3. So it was 3 for that special case normal distribution, but in fact, what this is telling us, because the kurtosis of the general normal random variable X, because that kurtosis does not depend on either of the two parameters of the distribution, mu or sigma squared, we see that every normal distribution has a kurtosis of 3. Now, likewise, let me back up a slide. And because the skewness of the general normal distribution does not depend on either of the two parameters, A or B, or equivalently, let's see, B or A, so the mean or the variance, which would be A squared, because the skewness does not depend on either of those, but it's 0, this tells us that every normal distribution has a skewness coefficient of 0, which is not surprising because we probably knew intuitively that every normal distribution is symmetric about the vertical line going through its mean. But this is mathematical confirmation that that intuitive idea is in fact true. Okay, and then finally, we derived the moment generating function for the special case of the normal distribution, but let's just go ahead and derive the moment generating function for the general normal distribution, not using integration, but using properties of expectation. And so by definition, the moment generating function of x is going to be the expected value of e raised to the tx power. And again, I can replace x with what it's equal to in terms of z, so a times z plus b. Then what I'm doing in going from here to here, I am distributing the t across both terms in the sum. And then I'm making use of exponent properties to decompose the exponential of the sum as the product of the individual exponentials. And because this e raised to the tb power does not depend on the random variable z, I can pull it out front. It's a constant, right, in terms of z. We then recognize that this expectation right here is just the moment generating function of z evaluated not at t, but at a times t. Now we know, we've already derived what that moment generating function looks like. And in this particular case, because we're evaluating at a times t, this moment generating function is equal to the exponential function evaluated at the square of the product at all over 2. We have like bases. We're multiplying, and so we can use properties of exponents. The exponents add in this case. And so this is the final version, or the final form, for the expression for the moment generating function for the normal distribution with a mean of mu and a variance of sigma squared. Okay, so to put all these results together, let's let x have a general normal distribution with mean mu sub x and variance sigma squared sub x. And I want to get back to using f for my PDF, so let's just denote the PDF and the CDF of the distribution of x by lowercase f and uppercase f, respectively. Then the PDF of the distribution of x, this general normal random variable, is given by this expression that we have derived here from the special case. And again, when we want to communicate that a random variable x has a distribution with this PDF, in particular, when we want to communicate the fact that a random variable x has a normal distribution with a mean of mu and a variance of sigma squared, we could just, express that by writing down this PDF. But it's a whole lot easier, a whole lot more succinct just to use this abbreviation, like we discussed before. Remember, the tilde is kind of the conventional symbol in statistics to use for the phrase is distributed as. And so we would read this as x is distributed as or according to a normal distribution with a mean of mu and a variance of sigma squared. Now, let me just point out that in some textbooks, in some resources, instead of listing the variance as that second argument, or that second parameter, they may list the standard deviation instead. Now, it may be fairly obvious in some contexts, but in others it may not. So you just need to understand what the convention is that's being used in the book or resource that you're referring to when you are reading that. Okay, now let's look at the CDF of the distribution, the general distribution. Okay, it's equal to the integral from minus infinity up to x of the PDF of the general normal distribution. Now the problem is, again, that there is no closed form expression for this integral, and so if we want to evaluate it, the best we can do is approximate it. Now, we're not going to have to do anything fancy to get that kind of an approximation. There are tables that we can use. Calculators will provide these values. And in fact, most, but not all, but most statistical textbooks include tables providing approximations for the values of the CDF. So in other words, if they're giving a table for the CDF itself, then they're giving a table for what we typically call left tail areas like this. Okay? Probabilities of the form, the probability that x is less than or equal to the argument at which we're evaluating the CDF. Other tables, other books give tables of this form, and we call these right-tailed tables. So they give tables that have probabilities where x is greater than a particular value. And still others, other books have tables that we might call central region tables. So the probability that the random variable x is between negative x and positive x. In addition, as I mentioned, several modern calculators include the CDF of the general normal distribution as a built-in function. And as an example, the TI-36X Pro has the normal distribution, the normal CDF built in, and so does the TI-84. And again, the moment generating function of the general normal distribution is given by this expression. And so this is a good expression to have in your notes. And then finally, for every normal distribution out there, and realize that there are an infinite number of normal distributions. Right? There's a normal distribution for every combination of a possible mean value and a possible variance. The mean can be any real number. The variance can be any positive real number. And so there are an infinite number of combinations of those parameters. And so there are an infinite number of normal distributions. But every normal distribution out there is symmetric about its mean. It has a skewness of 0, and every normal distribution has a kurtosis of 3. Now let me say one more thing about kurtosis and the fact that the kurtosis of the normal distribution is 3. We are using the actual definition of kurtosis in calculating this for not only this distribution, but the kurtosis of every other distribution that we've looked at in this course. Some textbooks, some resources, some software programs will tell you or calculate kurtosis in such a way that the kurtosis of the normal distribution is 0. Now, for those textbooks that do that, they're not actually calculating kurtosis. For software programs that calculate kurtosis, and I'm using air quotes here, okay, in that way, they're not actually calculating kurtosis. What they're calculating is what is called excess. EXCESS, excess. And what they're calculating is the kurtosis minus 3. So they're calculating what kurtosis as we're calculating, but then they subtract from that 3. And the reason they're doing that is because they're really what they're wanting to do is to compare the kurtosis of whatever distribution that they are talking about with the kurtosis of the normal distribution. And the easiest way to, well, I wouldn't say the easiest way, but one way to do that is to just calculate kurtosis and then subtract from that value the kurtosis of the normal distribution. And so what the result is, the distributions that have a kurtosis greater than 3 have an excess, it's positive, and distributions that have a kurtosis that is less than 3, in other words, less than the kurtosis of the normal distribution, then their excess is negative. And so that is, I guess, found to be appealing by some authors and people in some fields. But the problem is they typically don't call it excess, they call it kurtosis. And so technically that's not correct. Kurtosis is the ratio of the fourth central moment to the square of the variance as we have defined it and as we have been computing it. But I will also tell you that SAS, the software SAS, even when they calculate, or the value that they report for kurtosis is actually the excess. So it's just something that I want you to be aware of. What we are defining and calculating and calling kurtosis is the actual definition of kurtosis. Some other textbooks will say that they're calculating kurtosis, but if they tell you, if that resource tells you that the kurtosis of a normal distribution is 0, just keep in mind they're not calculating kurtosis, they're calculating excess. So don't be confused by something like that. Okay, so that is all we're going to talk about right now about the theoretical aspects of the normal distribution. So what we did was we started by looking at the special case normal distribution. And in fact, let me just say one more word about that. That particular special case normal distribution, we see that it has a mean of 0 and a variance of 1, and that has a special name. The normal distribution with a mean of 0 and a standard deviation of 1, and therefore a variance of 1, that is called the standard normal distribution. All right. And when we calculate probabilities involving a normal random variable, typically what we will do is we will reformulate that probability statement involving a general normal random variable into an equivalent probability statement involving a standard normal random variable. And the reason we do that is because the tables that we talked about here on the previous slide, tables for giving us values of the CDF and so forth, those tables are for the standard normal distribution. All right, so that's all we're going to say, and we'll pick up talking about another distribution in the next lecture video.